Okay, so we will be seeing some piecewise functions in this course, and then in future math courses. It's just sometimes one pattern is what holds for part of it, and then something else happens. In this case, the absolute value is something that's very commonly needed. It's like, what's the magnitude of something? Plus or minus 3. The size of that number is 3. No matter which way you look at it, it's just one of them is negative, the other one's positive, and the absolute value makes whatever you have positive. So just to use function notation, I'm going to use this as an example. I'm just going to let a of x be something that's equal to the absolute value function. So there are things we can do with this, and that is it's kind of a nice warm-up, and I want to do a couple variations on this. What happens if you take absolute value x plus 3 or something like that? So different things could happen that can kind of trip you up a little bit if you're not careful, but let's start with the basics. So let's just do a graph. So yeah, let's graph it. So well, literally the way that if you didn't already know what the absolute value meant, well, following the instructions says we take the input, absolute value of -2 is it's just the thing itself. If there's they don't write the word if here, but it's understood that if you see in the definition of a function, if you see these braces and then two different cases, it's understood that this is saying that you do this if x is bigger than or equal to 0. But they don't write if because it's understood that this notation means that that's what they're saying here. And we take the negative of it. So it's a little bit overkill. Like, I think usually you learn absolute values before you learn about piecewise functions. And we're like, no, that's not. First, you see which case are we in. -2 is, we're in case number 2, where we're plugging in a number that's less than 0, which means that's the definition of the function. So we get +2. -1 is, we're in case number 2. So we get +1. Same idea. Absolute value of 0 equals, well, now we're in case number 1. So 0 is greater than or equal to 0. So we just get 0. Absolute value 1 is, 1 is greater than or equal to 0. So we do the first one. So if 1 is bigger than or equal to 0, then the function gives you 1, and then same thing with 2. So you need at least this many points to be kind of certain that you have the right pattern, but if you do it very carefully to scale, you have your 1, 1 and your 2, 2. And well, this one I actually accidentally drew it. I didn't draw it quite. The scale is a little bit smashed over here, but let me make sure it's not deceptive. Let's make sure it's actually straight. Turns out it's actually straight because it's just 1, 1, 2, 2, 3, 3, and then -1, 1, -2, 2. So it's straight. Hits a sharp corner and it goes straight back up again, going to the left. So kind of like a laser beam. But that's it. So think, yeah, I think using if you already understand the absolute value, then just sort of doing it in your head is kind of a little bit more familiar, maybe a nicer way of doing it. Let's sort of do another one. All right, so we know that when the inside is equal to 0, that's kind of interesting. So the inside is 0 when x is negative 5. That's something you might want to keep in mind. So let's actually do that. So let's we know that when x is 0, interesting things happen. But let's just do it. So we have x, we have y. Let's try negative 5, maybe negative 6, negative 7. You plug in negative 7, y equals absolute value of negative 2 equals positive 2. Y equals absolute value of negative 1. So it's because it's negative 6 plus 5. You're getting positive 1 because it's the absolute value. Absolute value of negative 5 plus 5 is absolute value of 0, which is 0. And you can slow it down and actually compute it if you really want to be totally sure. But absolute value of positive 1 is 1. Absolute value of positive 2 is positive 2. So here's the x values that we're plugging in. The very first one, if I do it in detail, negative 7 plus 5. So a lot of the same things happen, but it's kind of centered at, it's kind of interesting. You might want to ask yourself, is this something that's kind of going to happen? Is this a pattern is this the kind of thing that happens for other functions where you plug in where instead of x, you have x plus 5? Seems reasonable to sort of guess that this might be a kind of a general thing. But here's minus 5. And then y is let's see, the y's are equally spaced roughly. Here's minus 3, and then here's minus 2 if I were to keep going. So here's minus 7, minus 8 would be up here. So yeah, if I wanted to include a couple more x's and y's, if I plug in x equals 0, I should get 1, 2, 3, 4, 5, which would be right here. But there you go. So it's yeah, so it's basically the same. All right, so let's do another one. I'm gonna erase up most of it. So I'm gonna define a new function, g of x, which is something else. So you should have paused or rewind and pause if you wanted to look at all that, but I'm going to erase most of this right now. And I'm going to have two problems here. So g, I'm going to call this other one h of x equals. Let's do the same thing. So last time it moved over 5 to the left, but I want to show you how to just do it from scratch. And then you can ask yourself whether it just moved 5 to the left. Is it really the same thing? But let's say let's make x equals, I don't know, let's make x equals 3 an interesting point. So let's see, what do I want to do with this for the other one? So when x is less than 3, let's make it x plus 3. Okay, so this one should be kind of interesting. Yeah, this one should be kind of interesting, so let's do it. X, y. So we definitely want x equals 3 to be kind of the center of our attention. When x is equal to 3, we're in case 1, so we get 6. When x is bigger than 3, we're still in case number 1. So we plug in 4, we get 8. We plug in 5, we'll get 10. So these are all x is bigger than or equal to 3. And then case 2, x is less than 3. So if we have a 2 here, we get, I'm going to make room for maybe just one more, just so we can see the pattern. So 1 and 0. So we plug in 0. 0 is less than 3, so therefore we get 3. If we plug in 1, we get 4. We plug in 2, we get 5. So 3, 4, 5. And the next one, it looks like it's, if you notice, this pattern kind of continues very nicely, and then this pattern also, they both kind of agree with each other, kind of like the absolute value. It looks like they hook up at the same place, which is really nice. What do we get here? So we get 1, 2, 3. If you watch the domain and range video, you can ask yourself, what kind of domain and range does it look like we're getting here? Here's 0. Am I going to have room here is the question. Let's make sure I have room. So let's make sure that the y has to at least go all the way up to 10 so I can fit the sample points. So here's 10, here's 5. Then 1, 2, 3, 4, 1, not quite equally spaced. Let's fix it. So 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. That's good enough, I think. Okay, when I plug in 0, I get 3. When I plug in 1, well, I guess I can, all my x's are positive for the sample points that I picked, so it looks like 0, 1, and 2. And actually, if you were to plug in this boundary point into this function, it would actually head towards, well, when we get to here, we're part of case number 1 when x is 3. So then when we're at 4, it jumps up by 2. It goes all the way up to 8. So it's like, when we're at 5, we jump up by, I think this one was a little bit too close. It should be, the tick mark should be a little bit farther away, so it should be all the way up here. So it's kind of like sloping at just, the slope is like 1, it's like 1. When in doubt, you can plug more numbers into your calculator. So if you plug in 2.5, you're in case number 1 and you get 5.5, you keep getting more and more, and you could, like here's case number 1, and then case number 2 is starting with, but it looks like the two pieces actually hook up with each other. And if you wanted to, you could plug in -1, you would get 2, like this pattern really is just a line that keeps going. And somewhere around here is where it would actually cross. But anyways, looks like the range looks like it keeps going because it's a positive slope, and then it's a steeper. Once x is at least 3, it's also sloping upward but faster. So the domain range looks like it's basically everything. So this point right here looks like it's really, really interesting. G of x looks like x equals 3. So G of 3 is interesting. So what I'm saying here is the most interesting point is G of 3 is interesting. So therefore, x plus 5 equal to 3 is very interesting for this h of x function. So well, let's do it. So we have inputs and we have outputs. So what's going to be interesting is for h of x, x plus 5 is the input, and when that's equal to 3, interesting things happen. So x equals -2 might be interesting here. So let's try that. And let's make sure we get interesting things. So -2. So h of -2 is equal to g of, you put a -2 in for x, but then you take this function g. G of 3 is this one, and you get 6. So this g is like a 2-part problem. We're referring back to what we just did, and we get this h of -2 on this new graph is 6. And yeah, so that's g of 3, and then let's see, we plug in -1. H of -1 is equal to g of -1 plus 5, which is it's these problems are a little bit, you have to slow it down and make sure you get it just right. Well, okay, so h of -1 is by definition g of 4. And then g of 4 is a piecewise function, and that's this piece. So 4 is bigger than 3, so we take 2 times 4, which is 8. H of, I wrote down the same number twice, so sorry. This should be a 0, and this is +1. So h of -1 is equal to g of -1 plus 5, which is g of 4. Oh, I just did -1, sorry. Now I'm doing 0. So h of 0 is g of 5, which is equal to 10. All right, so that's good enough. I wanted to do some other ones. H of -3 is g of -3 plus 5, which is g of 2. G of 2 is, we're not here anymore, we're down here. G of 2 is 5. H of -4 is g of -4 plus 5, which is g of 1, which is, here's what g is. G, the input is less than 3, so we're down here. which is positive 4. And, well, we have to make a brand new graph. Let's use the same axes. Do we have enough room? So -1, -2. Yes, let's just use, I'm going to use red for this one. So the old one, so here's y is equal to g of x. And it's like, yeah, you're kind of doing all the same things, but they're happening for different x values. But so when you change the input to make a new function, you get kind of the same outputs, but for the x's kind of all shifted around. So let's graph it. So for this function, y equals h of x, everything's going to get moved over to the left. So we get 0, 10. We get -1, 8. So we're getting this slant down here. -2, we get positive 6. Yeah, this marker is starting to turn black because the red marker touched the black ink. And then it's a steep, and then it's not as steep. So when we get to -3, we're only at positive 5. And then -4, we're only at positive 4. And so on. So it's something like that. So it's piecewise functions are a little bit tricky if there's a combination going on. So maybe there might be one like this, but this is one of the more out of the. Would be one of the more challenging problems, but for sure the part A, you should be able to graph a piecewise function. It's just know what the two cases are. And what does it look like here? Yeah. Yeah, so just be careful about a couple of things. I think I want to do one example where the pieces don't necessarily fit together. So here what happened was these actually agreed with each other when x was equal to 3. If you plug in 3, the piece that we don't use anymore still agrees with the original, which is really, really convenient, but sometimes that's not the case. So I want to talk about that. So now's a good place to pause it. I want to do a new problem, but I want to change this example slightly. So you want to pause it. I'm going to change a lot of things. So new problem, and let me give an introduction here. So when they don't join together nicely, when they don't come together, and there's this thing, this open and closed dot notation that we have to be very kind of careful about this. So here's what we can do. So let's say we had not x plus 3. Let's say we had x plus 5 when x was less than 3. So this work is everything. For x larger than or equal to 3, this problem is going to be exactly the same as the one that we did. But I'm not going to examine the h of x problem. And all of this is kind of out the window. So, well, I increased all the y values by a little bit. Let me show you what we get. Let's sort of, well, we can still fill out our table, but what happens here? We plug in x equals 0. Now we're getting 5. We plug in x equals 1. X is less than 3, so we get 6. So here at 2, we go all the way up to 5, 6, 7. We're up here. We're up here. We're up here. So far, so good. And if we wanted to plug in -1, we would get +4. Let me fix the scale here a little bit. So we're here. Yeah, so we could go all the way down here like that. That's all fine. These are all fine and good. But what happens when we get right here at the dividing line? We know that what we actually use is the closed dot that we put for the piece where x is bigger than or equal to 4. Well, what you can do is at x is equal to 3. So this is a good practice. The two pieces do disagree with each other, but we could figure out what we would get. 3 plus 5. So this is the right piece, the right hand piece. Well, the right hand piece wants to give us y is equal to 8, but we don't actually get there all the way there. So here's 10, here's 8. So we follow this straight line for the left hand piece. Sorry, not the right hand, it's the left hand. And this is really annoying to do by hand. It's a lot easier if the book just gives you a graph and they ask you a question about the graph. But how do you go from the algebra to figuring out how to draw the picture? Well, what you do is you plug in closed dots for sample points that are actually inside the left-hand piece, but when you're right on the boundary, one of the pieces actually corresponds to something that actually is happening on the right-hand piece in this case. But on the other piece, 3 is right on the border, and if we're on the wrong side of the border, we're following this pattern, but we exactly when we get to x equals 3, we're not following that pattern anymore. Well, it's really, really nice for drawing your picture to know where's the trend going. It's everything between 2 and 3. Those are points in the domain. Those are points that are all on the left-hand piece. Everything from here to everything between here and here, it all exists. You don't just stop drawing. That's not. You want to actually continue the pattern, but you also want to be honest that, hey, that is not a part of the left-hand piece. We're headed in that direction, but we don't quite get there. It's like we get arbitrarily close. We get closer and closer to x equals 3. Well, right when we're at x equals 3, suddenly we teleport. We fall like 2 stories down, and we're at y equals 6 all of a sudden. So the part where you have the equal sign is the part where you have the closed dot, and the part that's missing the equals is an open circle. It's nice when the two pieces sew together nicely and they join up and they agree with each other. It's all good. This time it didn't, and that's just that's just the mathematics. It's something that could happen. Something you might want to be aware of. I did not put one of these on homework 3, maybe on homework 4, but maybe not. I'll think about it. But if it comes up, you can look at this again, and that's kind of how you can do it. All right, so maybe it'll come up in this course, maybe it'll come up in the future, but there are some things that you want to be aware of. piecewise functions are a little bit weird in the end. Like half the secret to it is just slowing down and being very, very literal minded. Just always work your way backward through the definitions, plug in everything where it belongs, and when you're plugging in individual numbers, just sort of when you get to this step, whatever number gets plugged into your piecewise function, that's the thing that you plug in. You check to see which case you're in, figure out which case you're in, and then evaluate the number, and then maybe you're here if x is 5, or if x is -1. If x is +5, you're here, so it's like this. If x is -1, then you're in case 2 when you're here. So just sort of stay on top of that. Okay, so is there anything else I wanted to say about it? Let me just double check. I think that was yeah, that was basically everything I wanted to say, and then maybe even a little bit more. Yeah, I think there's something else I could say, but I think it would be overkill. I think this is good enough for what we need to do, and yeah, that should be good. So there we go.